Okay, guys, this is meant to be a quick review of the notes that we took over the course of the last few weeks. So, I'm not going over the first and the third law. You should be able to remember those. If not, look it up on the internet. But the main thing we need to remember is how to do net force. So first of all, if you'll remember, net force is equal to mass times acceleration. Okay? And so the way you do this is you take each section independently. So if like these are our forces, we have 4 forces here, we're going to treat the y's and the x's independently. And so for the x direction, for instance, we would do F4 minus F3 equals mass times acceleration. And in the y direction, we would do F1 minus F2 equals mass times acceleration. And keep in mind, this would be the acceleration in the x direction and the acceleration in the y direction. Now, generally in this one, there's a 100% chance it will either be in the x or the y direction. You're not going to have any movement in both directions on this test. So, in general, one of these accelerations will be 0, so they'll cancel out. Remember that if the acceleration is equal to 0, then the forces all have to cancel each other. Like, so for instance, here in the x, the forces would have to be equal to one another. Force 4 and force 3 would have to be equal and opposite to cancel each other out. Also remember that if the acceleration is 0, it can either be at rest or moving at a constant speed. You have 2 options there. Okay? The other option, though, is that the acceleration is not 0, and in the event the acceleration is not 0, then either F1 or F2, for instance, if we're dealing with the y direction, either F1 or F2 would have to be greater, and then you would get an acceleration. If F2 were greater, the acceleration would be negative, and if F1 were greater, the acceleration would be positive. Okay? So that's a general summary of net force. I feel if you don't take anything else from this page, please remember how we get from here to here, and remember this part. If the acceleration is 0, you're either at rest or a constant speed. Okay, force of gravity is otherwise known as the weight. So if you look at an object that's falling, the only thing acting on it would be the force of gravity. In that event, the net force equals mass times acceleration. Well, the only thing acting on it would be the force of gravity for a falling object, and the mass of that object times the acceleration of that object. Remember that objects that are in free fall accelerate at 9.8 meters per second squared. And so the force of gravity formula is just generalized as mass times 9.8. And so you can remember that. The weight will always be straight down. It will always be straight down. And since it's straight down, when you go to plug it into your Fnet formula, it will go in as negative. Okay? So the force of gravity will go into your formula as negative since it's going down. Next up, we have the elevator lab. Okay, in the elevator lab, you have an elevator, obviously, a scale, and a person standing on that scale. Okay. Now, the question is usually going to ask something along the lines of what is the force of the scale or what acceleration they're experiencing. It really doesn't matter what the question is. You start the same way. You draw the force of the scale up, and then you draw the force of gravity down. And then, after that, you can plug it into the Fnet formula that the force of the scale minus the force of gravity equals mass times acceleration. And then that, for any of these formulas, is going to be your base formula, right? That's what you're starting with. I'll write it just a little bit neater so you can see it. F scale minus force of gravity equals mass times acceleration. Notice if the elevator is not moving, or if it's going at a constant speed, the acceleration would be 0, and the scale would equal the force of gravity. If you're going up, the scale force would have to be bigger, and if you're going down, the scale force would have to be less. Now, a little note on conversions. If you get it into pounds, like let's say that your force of the scale is in pounds. Let's say it's 100 pounds, and your force of your gravity is given in pounds too. Let's say that's 90. Okay, you're going to have to make two conversions with these. For the force of if they give you the weight or the force of gravity to find the mass, you're going to take the weight and divide it by 9.8, and that'll give you the mass. To get the force of gravity and the force of the scale, multiply them by 4.45, or divide by, you know what, I'm sorry, I did the math wrong. The mass should be divided by, not 9.8, should be divided by 2.2. Got ahead of myself. 2.2. There we go. For the force of the scale, you can multiply by 4.54 or divide by 2.2 and then multiply by 10 or 9.8. Okay? Here we'll do 9.8 since that's technically what it is. Okay, so for the force on, if you're trying to get it out of pounds, the first thing you do is to find the mass. You're going to do the force of gravity divided by 2.2. So whatever you got. So in this case, we would do 90 divided by 2.2. For the force of gravity and the force on the scale, you're going to multiply those by 4.45 to get it into newtons. Remember, this gets it into kilograms. And then once you get it into newtons, you're good to go. Or you can divide it by 2.2 to get it into kilograms, and then multiply it by 9.8 to get it into newtons. Either way, you're ending up with newtons. Okay? And then once you get those two numbers, you can plug it into the formula up here. Okay? This right here is key. Alright, you've got to remember that. Alright, for the elevator problem. Okay? Next up, we have the normal force. The normal force, remember, is the force that is pushing up on that is pushing an object, keeping it from moving through whatever surface it is on. So, the first way to do the normal force is if the normal force and the force of gravity are in the same direction. When you get this, the Newton's second law, F net, would be normal force minus force of gravity equals mass times acceleration. So if it is not accelerating, the normal force is equal to the force of gravity. If the acceleration is not zero, then the normal force would be equal to mass times acceleration plus the force of gravity. Okay. But there's also a little addendum to this, because you could have two things pulling up on it, right? You could have something pulling up on it or something pulling down on it. And notice if we have like the puppet problem that was on the problem set, what it had was a force from a pull up, then the normal force also pulling up, and the force of gravity pulling down. And in this case, you do it the exact same way we do here. We're just adding in another up force. So it'd be like normal force plus the force of the pull minus the force of gravity equals mass times acceleration. And again, the normal force would be equal to mass times acceleration plus the force of gravity minus the force of the pull. And I'm just using this as an example. You could have something pulling down on it as well, right? Like we could have a situation where maybe you're pushing down on the box, right? Like a kid is pushing a box down onto the ground. Well, in that case, you would again have the force of gravity down, but then the force from the push also pushing down, and the normal force up. And in this case, you just got to do it again, but this time you've got it subtracted rather than added. Okay? There's all kinds of different ways you can do this. The important thing you need to remember is that you need to label all the forces. Okay? Let's see. I would like to point out that if you just don't know, assume that as long as you are on a horizontal surface. Alright? Like if you just don't have anywhere to go, you have no idea what you're doing, you don't remember any of the rest of this, if it's on a horizontal surface, remember that the normal force is equal to the force of gravity you probably will be able to get somewhere with that. All right. Normal force part 2. This one we're not going to see on this test, but it'll come up later, so I'll go ahead and show it to you. Is that when you have a box sitting on an incline, the force of gravity is straight down, but the normal force is always at a right angle to the surface, so it looks like that. And in this case, the normal force is equal to a component of the force of gravity. And we'll get into how that works a little later. And the third type of normal force is one of the ones that's on the problem set, and that's where you have a force being applied holding the object up against a surface. For instance, on the problem set, I'm not even going to try to draw it. It was the one where the two people were trying to hold the box with the hands. The more classic example is you have a block or a book or something. Call it a book. You have a book up against a wall, and somebody is pushing the book onto the wall to hold it onto the wall, right? Well, in this case, you have the force of gravity down, but notice that you have the normal force would have to be out from the surface of the wall. So in this case, if that book is not moving, the normal force is equal to the force that you're pushing, not the force of gravity. So in this situation, the normal force does not equal the force of gravity. Okay? Alright, moving on to friction. Okay, friction is a fairly simple formula. It's equal to mu times the normal force. Mu is the coefficient of friction. It'll usually be something, this is just an example, it will usually be a decimal number, but it won't have any unit. Okay, and it'll say in front of it the coefficient of friction is. Remember, there are two types of friction. There's static friction, and there is kinetic friction. Now keep in mind, first of all, the coefficient of static friction, when you plug it into the formula, gives the max value for static friction. You have to overcome this to move. So in order to move at all, you've got to overcome the static friction force from the formula when you plug in mu s times the normal force. Once you move, you are now governed by kinetic friction. And kinetic friction is going to be constant. It's going to be constant once you're moving. Okay. So anyway, this is the way static friction works. Now keep in mind, you can find friction, you don't necessarily have to use mu times the normal force to find friction, right? So like a car, if I tell you that a car is driving at a constant speed down the road, and this is going to be a terrible car, I apologize. Okay, so a car is driving at a constant speed down the road, and it has to apply a forward force of 1,000 newtons. What does the friction force have to be? Well, if it's going at a constant speed, you should remember that the acceleration is 0, and if the acceleration is 0, those forces should cancel out. So the friction force on this car should be 1,000. Once you find that, since the car is already moving, the friction force is just 1,000 in the problem, right? Since the car is already moving, regardless of what else happened. So if you need the friction force to solve another part of the problem, you would just go with 1,000 newtons, whatever it was to begin with. Okay? The last thing is the spring force. Spring force. Okay, so on the spring force, you're really just doing spring force is equal to kx. K is the K is the spring constant, and kind of like coefficient of friction was the same, was different depending on the surfaces. The spring constant is different depending on the spring. X is the distance the spring is stretched or compressed. Okay. Um, the way this would work is essentially if this is the normal stretch of your spring, and then you compressed it, that distance here would be your X value. Okay. If this is your normal spring, and then you stretched it to here, then this distance would be your X value. Okay, so that's how you find the X value. It's not the length of the spring, it's how far it is stretched. All right. Last note with spring forces, you can often use them to measure other forces. So think about like, how do you measure the fish you caught, the weight of the fish you caught? Use a spring scale. How do you measure the force you're pulling on if you ever use a torque wrench, that's basically a spring scale that you're using on a torque wrench. Anyway, my point here is that they're often used to find other forces because this rate is constant. The force increases at a constant rate, and so basically by measuring how much the spring is compressed or stretched, which happens at the regular rate, you can get a very accurate reading for the force that you're using on it. All right, so that is a 16.5-minute video over the notes. So if you need any help, feel free to let me know, and I will be happy to assist you.